Welcome to UBG Bytes.
Great to be here.
Today, we're diving deep into React Native. Now, this is the framework that lets developers build apps for both your iPhone and your Android phone, often using just one set of JavaScript code.
That's the core idea, yeah. You probably use apps built with it every single day. Think, Facebook, Instagram, lots of others.
Exactly. It's a pretty widespread. So our plan today is to sort of unpack what makes React Native tick.
Right, like how does it actually manage to work on both iOS and Android?
Yeah, how it bridges that gap. And then we'll get into something a bit more technical, maybe a little intriguing, the world of reverse engineering these React Native apps.
Which can be, well, let's say challenging sometimes.
Definitely. So think of this as your shortcut to understanding the basics of React Native, but also with a peek under the hood at some surprising details.
And understanding this stuff, even from a user's perspective, gives you a better sense of how the apps you use are built and maybe some of the security aspects involved.
Okay, let's start at the beginning then. For anyone listening who isn't, deep in the code weeds, what is React Native fundamentally?
So React Native came out of Facebook. Meta now, obviously.
Yeah.
They open sourced it back in 2015. It's basically a JavaScript framework specifically for building native mobile apps.
Native, meaning they feel like regular apps, not just websites in a box.
Precisely. The whole point, like we said, is write your code once in JavaScript and then deploy it on both Android and iOS, which you can imagine saves a ton of time and resources for development teams.
Right, two birds, one stone kind of deal.
Exactly. It tries to combine the best parts of native development with React, which is, super popular in the web world for building user interfaces.
And I hear the term components thrown around a lot with React and React Native.
Yeah, components are key. Think of them like Lego bricks for your app's interface. Reusable pieces, a butter, a list, maybe a whole screen section. They're kind of analogous to activities or fragments if you're familiar with native Android development.
Okay, like building blocks. And it uses something that looks like HTML, JSX.
That's right, JSX. It looks very much like HTML, but it's actually embedded right inside your JavaScript code. It's how you tell React Native what the UI should look like.
Okay, so JavaScript, JSX components. But how does that bundle of web-like stuff actually become a real functioning app on my quite different Android phone versus, say, an iPhone? That seems like the magic trick.
It does feel a bit like magic, but it's clever engineering. Your JavaScript and JSX code doesn't, directly become native Objective-C or Swift for iOS or Java Kotlin for Android.
Okay. So it's not a direct translation then?
No. Instead, React Native bundles a JavaScript engine, often JavaScript Core, or more recently Hermes, right inside the app itself. This engine runs your JavaScript code.
An engine inside the app?
Yeah. And there's this critical piece often called the bridge. This bridge is the communication highway between your JavaScript code running in its engine and the actual native platform components and APIs of the phone.
So if my JavaScript needs to use the phone's camera,
it sends a message across the bridge to the native side, which then talks to the actual camera hardware. The bridge translates those requests back and forth.
Got it. So the bridge connects the JavaScript world to the native world. So when a developer finishes writing their code and builds the app for Android, what does that physically look like inside the app package?
Okay, so when you build for Android, typically all that JavaScript code, all the logic, the components, everything gets bundled together into one single file. Usually it's called index.android.bundle.
One file holds all the JavaScript.
Pretty much, yeah. And this file is almost always minified.
Minified meaning squished.
Squished is a good way to put it. All the extra spaces, comments, long descriptive variable names are removed or shortened to make the file as small as possible. Helps with load times and app size.
Okay, so a big, dense JavaScript file. And I assume iOS is something similar.
Correct. A similar process happens for iOS, creating its own bundle file. But focusing on Android, that index.android.bundle, you can think of it as the heart, or maybe the brain, of the React Native part of the app. All the custom logic written by the developers lives in there, in that condensed JavaScript form.
Right. So if someone, maybe a security researcher or just a very curious user, wanted to understand how a specific React Native Android app works, that bundle file is ground zero.
Absolutely. It's the primary target.
Yeah.
Because all the app's unique behavior and features are defined in that JavaScript, analyzing the bundle is key to understanding what the app actually does.
Okay, so how does one typically get their hands on this file and start looking at it? It's not just sitting in a folder I can browse on my phone, right?
No, not usually.
Yeah.
The traditional approach involves a few steps. First, you need the app's installation file, the APK for Android.
Okay, get the APK.
Then, a common first step is just renaming the .atk file extension to .zip.
Really? Just rename it.
Yeah, because APKs are essentially zip archives. Renaming it lets you open it like a regular zip file and see the contents.
Oh, okay. Then what?
Inside, you'll find various files and folders. To make things more readable, especially the non-JavaScript parts, people often use a tool called APK tool. It decompiles the app, breaking down some of the compiled Android components and resources into a more human-readable format.
Decompile. So trying to reverse the building process.
Exactly. And once you've run APK tool, you can navigate the extracted file structure, and usually within the assets folder, you'll find it, the index.android.bundle.
And then you just open it in a text editor.
You can, but remember the minification step we talked about.
Ah, right. The squished code.
Yeah. So what you'll see is likely a massive wall of JavaScript, maybe all in one line, with cryptic single-letter variable names. It's not exactly easy reading. Understanding the logic from that requires quite a bit of effort and sometimes specialized tools to help format it or prettify it.
Like trying to read a book with no spaces or punctuation. Okay, so that was the traditional challenge. But then things got even more complicated with something called Hermes, right?
That's right. Hermes really changed the game for reverse engineering React Native apps. See, Meta developed Hermes as their own custom JavaScript engine, specifically optimized for running React Native on Android.
Optimized how?
The main goals were better performance, faster app startup times, using less memory, and reducing the overall size of the app compared to using the standard JavaScript core engine.
Okay, sounds like good goals for users and developers, but bad for reverse engineers.
Well, here's the kicker. When an app is built using Hermes, the index.android.bundle file often isn't just minified JavaScript anymore. It's compiled into Hermes bytecode.
Bytecode. That sounds less like code and more like machine language.
It's definitely a step closer to the machine. It's a lower-level representation of the original JavaScript, optimized for the Hermes engine to execute quickly, but crucially, it is not human-readable JavaScript.
So if you open a Hermes bundle,
You'll likely see what looks like gibberish, a stream of characters that don't make sense as text or standard code. It's a completely different format.
wow. So Hermes, while boosting performance, basically put up a big wall, making it much harder to just look at the bundle file and understand the app's logic.
Exactly. It, as one source put it, threw a wrench into the gears of many reverse engineers. The days of just needing to prettify, minify JavaScript were suddenly over for a lot of modern React Native apps.
Okay, but the reverse engineering community is pretty resourceful, I imagine. Surely tools started popping up to deal with Hermes bytecode.
Oh, absolutely. Where there's a challenge, people start building solutions. Several tools have emerged specifically to tackle Hermes bytecode. One of the earlier ones is HBC tool.
HBC tool, what does that do? Does it turn the bytecode back into JavaScript?
Not quite back to JavaScript. That's the really hard part. What HBT tool does is disassemble the Hermes bytecode. It translates the binary bytecode into a human-readable bytecode format. Think of it like getting assembly language instead of the original high-level source code. It's still low-level, but it's structured text you can actually read and analyze. HBK tool works particularly well with some of the older Hermes versions like V85.
So how would you use it? You find the bundle file.
Right. You decompile the APK, find the Hermes bundle file, then run HBK tool using its atamsasm command, pointing it at the bundle. It outputs the disassembled code, usually into .hasm files, along with extracted strings and metadata.
Okay, so .hasm files give you the low-level instructions. Still not easy, but better than gibberish. What else is out there?
Another tool is Hermes deck. This one has ambitions to both disassemble and decompile.
Ah, decompile meaning getting closer to actual JavaScript.
That's the goal. The disassembler part of Hermes deck is apparently quite good and designed to be adaptable for newer Hermes versions. The decompiler part, however, aiming for that JavaScript-like output, was reported as not fully developed, at least as of late 2024. Still a work in progress on that front.
Gotcha. Good disassembler, maybe someday decompiler. Any others?
There's Hasmer. This is another project described as promising, but maybe still under active development. It's interesting because it includes things like a VS Code extension and features to help it adapt to new Hermes versions. It can disassemble and assemble bytecode.
Assemble, so you could potentially change the bytecode instructions and put it back together?
That's the implication, yeah. Which opens up possibilities for modifying app behavior.
Okay, one more.
Lastly, there's Hermesers. The R suggests it's written in Rust. It's noted for being dependency-free, which is nice, and supporting a range of more recent Hermes bytecode versions, like V89 up to V96. It seems like a capable, modern option for disassembling and assembling.
So it sounds like there are tools, but it's maybe a bit fragmented, dealing with different Hermes versions, some tools doing disassembly, others trying for decompilation.
That's a fair assessment. While these tools are great, the overall situation for reverse engineering, and especially for dynamic analysis like watching the app while it runs, is still often considered lacking compared to what's possible with purely native apps.
Lacking how?
Many tools might be out of date with the very latest Hermes changes, or support might be incomplete. It's a moving target because React Native and Hermes keep evolving. The tooling for native apps has had much longer to mature.
Right, it's a constant catch-up game. Now, you mentioned dynamic analysis. One source brought up using a tool called Frida for this. What's that about?
Yeah, dynamic instrumentation with Frida is really powerful. Frida lets you inject your own scripts into a running application process.
Inject code into a running app. Wow.
Yeah, so for a React Native app on Android, you can use Frida to hook into the React Native runtime environment itself. There's a specific Java class, Catalyst Instance Impl, that's often targeted.
Hooking, like tapping into its communication lines.
Kind of, yeah. You essentially intercept function calls or gain access to the app's internal while it's executing. You can inject your own JavaScript into the app's JavaScript context.
What would you do with that?
Well, you could, for example, list all the global variables the React Native part of the app is using. Or you could monitor network requests by hooking the JavaScript functions the app uses to talk to the internet, like XML HTTP request.
So you could potentially see data being sent and received?
Exactly. You could log requests and responses. React Native apparently even has some built-in network interception capabilities you can sometimes enable. You could also hook JSON.parse and JSON.stringify to see the data structures the app is working with.
That seems incredibly useful for understanding data flow.
It is, but it gets even wilder. Some research explored interacting directly with the app's UI elements from injected code.
Oh.
By digging into the internal React Native data structures. One researcher apparently found the object representing a button on the screen and was able to programmatically trigger its onPress handler, basically, clicking the button from their injected script.
You're kidding. So you could potentially control parts of the app's interface remotely without actually touching the screen.
That's the implication. It shows how deeply you can potentially interact with the app's internals once you have that foothold with dynamic instrumentation. It really highlights how the UI is represented internally within that JavaScript environment.
That's mind-bending. So given all these tools and techniques, bytecode disassembly, dynamic instrumentation, can developers really protect their React Native code? Is anything truly safe on the client side?
That's the perennial question, isn't it? And the general consensus echoed in that Reddit discussion we saw is basically no. Client-side code, whether it's web JavaScript or a mobile app bundle, fundamentally runs on a device you don't control.
The user's device.
Right, so determined individuals can analyze it. Obfuscation, making the code deliberately confusing, and using things like Hermes bytecode definitely raise the bar. They make it harder, slower, more annoying.
But not impossible.
Not impossible for someone sufficiently skilled and motivated. It's more about deterrence than absolute prevention.
So the common advice is?
Don't put your crown jewels in the client-side code. Sensitive stuff, secret keys, core proprietary algorithms, critical business logic should live on a secure back-end server that the app communicates with, not inside the app bundle itself.
Keep the secrets on your own machines, not the users. Makes sense. Okay, so let's wrap this up. What's the main thing you want listeners who are mostly users of these apps to take away from all this?
I think the key takeaway is that React Native is this really efficient way to build apps for multiple platforms, but its architecture, using that JavaScript bundle, the bridge, and now engines like Hermes, creates a unique situation.
Unique challenges and opportunities for understanding how they work.
Exactly. Reverse engineering is possible, tools exist, but it's an evolving field, especially with Hermes constantly being updated. It's not always straightforward.
And this dynamic instrumentation stuff, being able to observe and interact with a running app, that opens up really interesting avenues for security research and just understanding app behavior, right?
For sure. It allows for a much deeper look than just static analysis of the code. But for you, the user, the bottom line is probably that while developers do try to protect their apps, the code running on your phone isn't in a locked vault. Determined efforts can often figure out how it works.
It's a good reminder about where sensitive operations should ideally happen, not on our phones.
Precisely. The client side is inherently less secure than a controlled back-end server.
Well, this has been super insightful. It really paints a picture of this constant evolution in mobile development and the efforts to both build efficiently and understand the results.
Absolutely. And if any listeners are technically inclined and curious, checking out some of those tools we mentioned, HPP Tool, Hermes Deck, Hasmer, Frida, could be a pretty fascinating journey.
Definitely food for thought. This has been another Byte by UBG.